Hello boys and girls, and welcome to our next video lesson on VSEPR. Yes, that's how we say that. It looks like VSEPR, but we say VSEPR. VSEPR theory will help us understand the shapes of these molecules, because remember what we said in the last video, structure determines function, or I like to say structure predicts behavior. And so if we know what the molecule is shaped like, we can predict how it will behave. So, what in the world is VSEPR or VSEPR, as I say, as most people say, not just me, everybody says it, so join the crowd. V stands for valence, you know, like valence electrons. S stands for shell, like energy level. We used to call energy levels shells, but now we call them energy levels. E stands for electrons. P stands for pairs. You should have gotten used to seeing pairs in your Lewis structure. And R says repulsion, stands for repulsion. Why does R stand for repulsion, or why do we care about repulsion? Because remember, electrons have the same charge, and if they have the same charge, they repel each other. So we can determine the shape of the molecule based on how the electron pairs push each other away, try to get away from each other. Well, what keeps the molecule together? Well, the nucleus has protons, and those protons hold everybody together. Okay, so now that we know what that stands for and that this helps us predict the behavior, what do? Well, we need to memorize this little chart. Here it is. Right now, I would recommend you pause the video and you copy this chart down. What we're going to do after that is we're going to go through and draw each one, and I'm going to show you how to identify the number of sides occupied and the number of lone pairs on the central atom. The number of lone pairs on the central atom. Okay? So, pause, copy. Good, excellent. So, let's start with our first example, CO2. What does carbon dioxide look like? So the first thing you need to do on carbon dioxide is draw the Lewis structure. Carbon has 4 valence electrons. Oxygen has 6, but there are 2 of them. So that gives me 6 times 2 is 12 plus 4 is 16 total valence electrons. So now we're going to draw the Lewis structure for carbon dioxide. I've done it before, so I can do it faster than you. You may need to erase some dots and add some double bonds and whatnot. Now, when we try to determine what the VSEPR shape will be, all we need to do is look at the central atom. That is the key. The key is the central atom, and carbon is the central atom. So we look to see how many sides of carbon have something occupying that side. So let's look. How many sides of carbon is occupied? Is there anything on the bottom? No. Is there anything on the top of carbon? No. So those are not occupied. Is there anything to the left of carbon? Yes. And is there anything to the right? Yes. Doesn't matter whether that is a single bond, a double bond, a triple bond. I'm just looking to see if one of the sides has something on it. And carbon has 2 sides occupied. That's why we're up here in the chart. We're on 2 sides occupied. Looking at carbon, how many dots does it have on it in the middle? No dots. That means no lone pairs. A lone pair is a pair of dots that are alone. They're not doing anything. They're not participating in bonding. On the central atom, carbon has no lone pairs. That means the shape of the molecule is linear. So what does the carbon dioxide molecule look like? It has a C in the middle, and it's bonded to an O, which is bonded to another O. Now, as a rule, if you want to, when you draw your VSEPR structure, if you want to, you may leave out lone pairs on the outer atoms. Not the central, outer. I underline the word outer. You can leave out your lone pairs on the outer atoms. So, what if I go to Google Images and I pull up a carbon dioxide molecule? What will that look like? Okay, so that took a second. I did not like doing that. Luckily, I paused the video, so you didn't even know it took a second. It happened in an instant in your world. Isn't it nice in your world? Comforting, fun. This is the carbon. Come on, computer. This is the carbon in the center, and here's one of the oxygen. Here's the other oxygen. Does this look like a little caterpillar to you, like all lined up? Yes, they're all lined up. That's why we call this shape linear. Just for fun, put a little antenna on it. Here we go, some feet. Here we go. So the carbon dioxide molecule, because it has no lone pairs on the central atom and 2 sides occupied, is considered to be linear. Let's go to our next example. Our next example is trigonal planar nitrate. That's the nitrate ion that you're familiar with. So the formula for nitrate is NO3 minus 1. Let's figure out our valence electrons. 5, 6 times 3, and negative 1 means took 1, so we're going to add 1 to our total. So that gives me 24 valence electrons. Lewis structure looks like this. I'm going to do it really quickly because we need to do VSEPR, not Lewis structures. You should have mastered these by now. And we put it in a bracket because it's an ion. Don't forget your brackets on your ions. So now when we look at this, we look at the central atom and we say, okay, how many sides of nitrogen are occupied? 1 side, 2 sides, 3 sides occupied. So we go to our chart and we see that 3 sides occupied, and it has no lone pairs. It has no lone pairs. If it has 3 sides occupied and no lone pairs, that shape is called trigonal, not triangular, trigonal planar. And here's what the molecule looks like. I'm going to draw it for you in trigonal planar. We put it in. We divide them up evenly to make a triangle, because if 3 sets of electron pairs are pushing each other, how can they get as far away from each other as possible? They can make that triangular arrangement. And so this oxygen pushes on this oxygen, these lone pairs on these atoms, and these guys push on these guys, and these guys push on these guys, and they all spread out into that triangular shape, which we call trigonal pyramidal. Notice I left out the electron pairs on the outer atoms because I don't like to put them. Cool? Cool. Let's go to our next example. Okay, so our next example, I had to change the chart. If you've looked at the chart now, you're going, oh gosh, I wrote in pen. I've got to scratch that out because I just realized as I was drawing that the chart wasn't quite perfect. So here we go. Now we've got 3 sides occupied and 1 lone pair. Our example is SO2. I'm going to scroll down, insert some extra writing space, and I'm going to draw the Lewis structure for SO2, sulfur dioxide. Sulfur has 6, oxygen has 6, there are 2 of them. That gives me 18 valence electrons. And so in the Lewis structure, I'm going to put that and that. I don't remember how this one goes, so I'm just going to do this one the old-fashioned way, just like you have just practiced, that you have just been doing. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Too many electrons, so I'm going to take a pair off here and a pair off here and add a double bond, and that is the Lewis structure for sulfur dioxide. So then I'm going to look at my central atom. I'm going to say, okay, what's around the central atom? How many sides are occupied? The central atom has 1, 2, 3 sides occupied. How many lone pairs does the central atom have? The central atom has 1 lone pair. And when I get that, our chart tells us that that is bent. 3 sides occupied, 2 lone pairs gives me a bent molecule. What is that going to look like? It looks a little like this. I like to put my lone pair on top, but technically it doesn't matter. And I'm going to go over here and over here. You should see, boys, girls, men, and women, that looks a lot like our trigonal planar shape we just did. The only difference is we took off that top oxygen and replaced it with a lone pair. That lone pair still pushes on the electron clouds of these outer atoms, and so still everyone's trying to get as far apart from each other as possible because electrons are negative and negative repels negative. Truth be told, this lone pair does affect this bond angle slightly. So up here, the bond angle is 120 degrees. Down here, it's a little bit less than 120 degrees because that lone pair pushes a little bit harder on these guys, kind of in that direction. I'm not really particular with bond angles, so don't worry too much about bond angles. Okay, so let's go to our next shape. Our next shape is 4 sides occupied, no lone pairs. That's called tetrahedral. You should recognize the tetra in here, tetra for 4. And our example for that is CH4. So let's come down. Let's draw CH4. CH4 has a really easy Lewis structure. You'll probably start to write this one without even showing any work. It's just this, a C with 4 H's. That's methane, in case you're curious, the main component of natural gas. All right, so when you look at methane, you say how many sides of the central atom are occupied. I'm not looking at the outer atoms. I'm only looking at central atom. 1, 2, 3, 4 sides occupied. How many lone pairs on the central atom? None. That's correct. Did you talk to your computer? I hope you are answering these questions. So 4 sides occupied, no lone pairs is tetrahedral. What does tetrahedral look like? This one is really funky. This is my favorite one to draw. You put your C in the middle, and we go up here, over here, over here, and a little bit shorter in the middle. Now, technically, that's not the way you'll draw it in college. It looks like this angle is bigger than this angle, but technically all the angles are the exact same. In case you're curious, that is a 109.5 degree bond angle. In college, you'll draw it a little bit differently, but we don't need to get quite that picky. I'll show it to you, though. You'll draw one here, and then over here you'll have a triangle, and over here you'll have this little doodad. I'm not sure what it's called. What that attempts to do is show 3 dimensions, because I'm drawing this, we're drawing it in 2 dimensions, but we have to visualize it in our mind in 3 dimensions. So be thinking 3 dimensions, like this H is coming out of the page at you a little bit. One day we'll have 3D computers and we can do this in 3D. That'll be awesome. It'll be great fun. Next up, 4 sides occupied. Note I changed the chart. If you didn't change your chart, make sure you do. And 1 lone pair. That's called trigonal, pyramidal, and NH3 is our example. Let's scroll down. Insert some extra writing space. NH3. That's a very easy Lewis structure. Note that all of these begin with the Lewis structure. What happens if you mess up the Lewis structure? Yes, you mess everything up, so don't mess that up. Don't mess that up. So, when we have ammonia, NH3, we look again. We're going to count. I'm counting with you. 1, 2, 3, 4 sides occupied. 4 sides occupied. And then I'm counting how many lone pairs I have. Oh, look, there's just 1 lone pair. 4 sides occupied and 1 lone pair gives us the shape trigonal. Where do they get trigonal from? Because there are 3 elements. Pyramidal. Where do they get pyramidal from? Because it makes like a little pyramid that stands up. It's basically the exact same as the tetrahedral we just drew, but what do we take out this time? We take out that top H with that bond and replace it with a lone pair. That's what trigonal pyramidal looks like. Remember, this is 3 dimensions. This H is coming out of the page, so to speak. If you could build this molecule, which we will in class, it will stand up like a little pyramid. Hence the name, pyramidal. All right, our last example is 4 sides occupied with 2 lone pairs. That makes bent, and that example is water. Water. Let's draw water. So water is H2O. The Lewis structure, actually, we did as an example when we first learned Lewis structures. Looks like that. Some of you might draw water a variety of different ways. You might put the H over here and the H down here and the lone pair here and the lone pair here. It doesn't matter, but because the Lewis structure gives us who's bonded to who, but not necessarily the exact shape. It's VSEPR theory that gives us the shape. So what shape do we get? 2 lone pairs, 2 bonds, or 4 sides occupied, 2 lone pairs gives us a bent shape. We're just going to take this ammonia and kind of repeat that with the water. We're going to put an O here. We're going to keep that H just like that one up here, just like that guy. And we're going to keep this H just like that guy. Whoops, I accidentally erased the O. We're going to keep the O, because without O, where would we be? Oh my gosh. And then we're going to replace that bond with a lone pair, and then that top bond with a lone pair. This shape is bent. You say to yourself, self, Mr. Walker already said bent once. Yes, there's kind of 2 kinds of bent. There's a bent based off the trigonal planar geometry, and there's a bent based off of tetrahedral geometry. Both of them produce a bent molecule. You should notice that this one is bent a little bit more than the trigonal planar bent. This is 109.5 degrees, except these lone pairs push more on that, so it's actually a good bit less than 109.5. Those lone pairs, these mean lone pairs, squeeze these hydrogens together to make it, to decrease that bond angle. That's not super important. Roughly 109.5 degrees is close enough. Okay, one last example. What about carbon monoxide? I didn't do an example like this. I only have 30 seconds of record time, so I'm going to pause and then it's going to magically appear. Okay, so a lot of stuff just magically appeared to you. If you have only 2 elements, in other words, there's no central atom, what shape do you have to be? You have to be linear. So whenever you have only 2 elements, the shape is linear. Be aware of that. That's the end. Thank you for listening and writing careful notes. Bye-bye.